All right. Good morning, everybody. Thanks for being patient with me as we work through the internet issues. Okay, so last time we were going through some basics in R, and we'll continue to do that today. We'll pick up where we left off last time. So we just finished talking about conditional statements, the if and else's. Hopefully everyone's got that straight. We'll continue on. We're going to talk about for loops, and then we're going to try and combine a bunch of stuff that we learned from last class. Okay. So, all right, so what we will do is look at for loops. Give myself a little more space over here. Loops and apply functions. For x in 1 to 10, print x. Okay, so this is a sort of particular type of thing you can do in R and also common in other programming languages. For loops are generally these pretty powerful tools that allow you to sequentially walk through a set of whatever you specify, and you can do it sort of many times. So in this case, all we're doing is you're defining some value x, and you're going to walk through all the things that happen inside the for loop, which is everything in the curly braces, and you're just going to print x. So this should print what? 1 to 10, exactly. So it'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So let's see if that happens. I'll select this and run it, and it'll just kind of print through. So one thing to note here, in our global environment over there, we see a variable x that is now defined, and that is 10. It's actually 10L. We'll talk about what that means in a little bit. Don't worry about it for now. But this means that the for loop operates in your global environment. Okay, this isn't like a function like before. So whatever happens inside the for loop, if you like define something in the for loop, that's going to show up in your global environment as well. It's not working in some kind of local function. So for example, let's say I do some for loop x in 1 to 10, and I do y is, let's do y is 1 plus x. So what do you guys think is going to happen here? You don't think it'll do anything? Okay, so we have one person saying it's going to make a list. We got one person who says it's not going to do anything. Any other guesses? Ah, yes, interesting. So, okay, so if you printed y, it would show stuff, right? Because if I just did, let's say, let's do y is 1 plus x here, nothing is going to happen, right? Besides the fact that y gets defined, but it doesn't show the answer over here because you're just doing an assignment. So let me Let me remove that y. So it's not that nothing will happen. Actually, something will happen. I've run it. Nothing got printed, but I did define y. And the y is going to be the last thing in the loop. Okay. So what about if I changed y, or changed the 1 to y over here? What do you guys think? Let me remove, let me start out by defining y as 1 over here. Or let me do it y as 0, not 1. So the easiest, we're going to start getting into more and more complicated loops. And maybe for this particular one, it's like too simple. Well, I'm not even going to say it's too simple, but generally sort of a good practice to start to figure these things out is to just write it down, okay? So what I'm going to do is make a table that helps me walk through and understand what's happening inside the for loop. Again, this is like a really simple example, but you're going to see as we get a little bit more complicated, understanding what's happening inside a loop is going to be much better if we do this. Okay, let me actually stop sharing. Okay. So I have my x's and my y's. So 1, 2, 3, 4, 5, onwards down to 10. Okay. In the first time that I step through my loop, my x will have a value of 1. I guess maybe I should clarify. I don't think I explicitly define this, but what's essentially happening is in the for loop, x in 1 to 10, it starts at 1 and it goes through all the values that you say on the sort of other side of the in, okay? So it's 1 in the first one. So what will y be after the first loop? After the first loop, it'll be 1, right? Because y starts at 0, x is 1, y plus 1 is 1. Okay, so now y is 1, x is 2. What happens after this? 3. Okay, and then 3 plus 3, 6, 10, 15, and so on and so forth, right? So that is what will happen here. Let me go back to sharing this screen. Okay, so if I run this for loop, our y should be equal to 1 plus 2 plus 3 plus 4 plus 5 all the way to plus 10. And that's indeed what we see. No, that's not what we see. Oh, nope, sorry. I didn't run the right line. Okay, there we go. So y is equal to 55. Okay, another way that you can check the for loop is to do what you guys said, is I'm going to go ahead and print y inside the for loop. So every time that it walks through, it's going to print the answer for that particular instantiation of the loop. So here, oh, wait, got to reset it. Okay. 1, 3, 6, 10, 15, and so on up to our final answer of 55. Great. Any confusions? Because we're going to get a little bit more complicated now. Okay. So I am going to copy and paste a longer function here. And we'll talk about this function. And you guys can have a little bit of time to try and interpret this. What is do? What does this do? Okay. Cool. So I've written down this function, and I would like a volunteer, please. Anyone? Yes, great. So I'm not going to ask you what this does right away. I just want to walk through this, and then we'll go line by line and try and interpret what's happening here. Okay, so I have a function, and I put in an input x. Okay, I don't know what the input is yet, but let's take a look. So the first line, so if x is less than 2, so what's happening here? Like, okay, what happens if I put x as 1 into this function? Will I enter the if statement? Yes. Yep, exactly, because x is less than 2. So as a reminder, as soon as you hit any return, the function ends, and that's it. Okay. So if I put x is 1, it will stop and it will say false. Great. What about if I put x is 2? Okay, great. That's right. Actually, let me not say x is 2. Let me say x is 6. Yeah, so it'll go to the next one. So we go to the for loop, right? Okay, so now in this for loop, okay, we have this weird thing happening for n in 2 to x minus 1. So if x is 6, what does the for loop do? We're unsure, right? So we'll do, let's write it down. Okay. So x is 6. And actually, let's do this all the way properly. So x equals 6. And our for loop is going to create this thing n. And what n's will we look at? Two to 5. So we're going to look at n 2, 3, 4, 5. Okay. Yes. I have not explained what this is. Percent is what is the term for this? Modular. Yes, thank you. And a modular is?
It's whether or not there's a remainder.
Yes, it gives you the remainder. So what's 3 divided by 2? It's 1, so it equals 1.5, right? And if you're in grade school, this equals 1 remainder 1, right? And if you do 14 divided by 6, this is equal to 2 remainder 2. Okay. So this is your modular here. So if you do 3 mod 2, that equals 1. If you do 14 mod 6, that equals 2. Everyone follow along? Okay, so what happens here is that you're going to walk through x mod n. So we're going to do 6 mod. Yes, sorry. Yes, okay. So for n, so it's going to do 2 colon x minus 1. So 2 colon x minus 1. So this x is 6. So 2 colon 6 minus 1. So 2 colon 5. And so this is going to say, make n go from 2 to 5. Make sense? Great. Anyone else? Okay. So now I'm going to do this test. X mod n equals 0. So 6 mod n. Okay, what's 6 mod 2? 6 divided by 2, what's the remainder? 0. Okay, 0. Okay, so I've now entered my for loop, and I'm going to return false. So this is false for my thing, but I actually hit return, so now I stop. Function is done. So, okay, what do we know so far? If I put in x equals 1, this ends. It's false. If I put in x equals 6, this function will return false. Shall we test some more values? What happens if I do x equals 7? So x equals 7. X equals 7 here. So 7 mod n. What is 7 divided by 2? What is there a remainder?
1.
Yeah, so the remainder is 1. What about 7 divided by 3? Okay, I'm going to stop saying divide. 7 mod 3 is 1. What about 7 mod 4? 3. 7 mod 5, 2. 7 mod 6, 1. So I've walked through all of these. It never enters here because the mod is never equal to 0, right? There's no 0 on this side. So then I go back over here. I'm done with the first part. I'm done with the second part. I get here and I say true. So 1 is false, 6 is false, 7 is true.
Prime number? Oh, prime number.
Prime numbers. Yeah, right? So this function will divide. So what's the definition of a prime number? Yes, it can only be divisible by itself in 1. So we know that 1 will return mod 0, and we know that the last one will return mod 0. Everything in between that can't be mod 0, right? Otherwise, it's not a prime number. So this function is a famous function in computer science. We call this, oh, let me share my screen again. Man, managing Zoom in the middle of class. It's fun. So this function is canonically called is prime. Yes, is it prime? So yeah, if you're coming from like a computer science background, this type of exercise is pretty common where we kind of look at functions, try and figure out what they do. And it's a good sort of exercise for people to get really comfortable and familiar with the language. Being able to interpret the code is really important to making sure that you understand what's going on. So let's go ahead and run this. Yes. Yeah, hang on. Okay, let me bring up my trusty pointer. Okay, so so you've got all these brackets, right? So those brackets can really kind of go anywhere. R is a type of programming language that doesn't really care about white space, which is all the like how you arrange things relative to each other. Whereas other programming languages like Python do care about that. However, it's generally good practice to arrange it in this sort of way. And what I mean by this sort of way is you'll notice that as I do one of these functions or ifs or for statements that do have curly braces, I'm typically always going to start the curly brace immediately and then close it on its own line. And everything within the curly braces is going to be, this is kind of my practice, but it's a pretty standard type of thing to do, is to indent everything within that set of braces. So you can really, I think, easily tell what's being contained within each thing. So here, this function, everything that's single indented is contained within that function. And let's look at the next one. So there's an if statement here. Immediately on that line, I have a curly brace and I give it a curly brace on its own line. And then everything inside is indented once again. So the thing that I can immediately see as being within the if is that return statement. And you can do this as many times as you want, right? Here we have a nested thing where we have the for loop, curly brace, and then its own curly brace on its line. But then we have another thing inside here that's indented. So there's two indents for the thing, for the if statement inside. So that's kind of considered a good practice so that I can pretty easily visually tell what's going on. Okay. So yeah, as I was saying, this is one of the things that you'll get good at. Maybe not in this class, although there's definitely going to be some more of this sort of interpretation. Okay. Let's talk about the concept of efficiency. Oh yeah, so sorry, go ahead. Nope, you do not. So yeah, actually, sorry, I was going to do this. We'll test that, right? Let me see. So I'm going to remove x. Okay, make sure I define this function and run it. Oh yeah, so really quickly, the shortcut that I was saying, you can run a line. So if you control enter or command enter if you're on the Mac, the line that you define the function, it will boom run the entire thing. Okay, it won't just run that one line. So anything with curly braces, it'll run the whole thing within the curly braces. Okay, you don't need to define x ahead of time. And in fact, I've removed x, so you can see there's no x in the global environment anymore. And let's see what happens. Let's do is prime 1 false, is prime 6 false, is prime 7 true. Great. And in fact, I can go ahead and make a for loop to test this. I could say for x in 1 to 100, print. I'm going to print two things. I'm going to print x. Oh, not print. Print x and print is prime of X. So what's going to happen here, guys? It's going to try and test all of the numbers between 1 and 100. It's going to print false if it's not a prime number, and it's going to print true if it is. So let me go ahead and run this. Okay, cool. And you can see here in our console, in a really inefficient way, we've gone through and printed all these. 97 is a prime number, but none of the guys over here are. And we can scroll up to see the rest of them. Yeah, so you can see which ones are true and false. Great. All right. Let me do something here. Okay. Yes.
Like, I was wondering about number 2. So I'm getting false for number 2. Like if I say is prime 2, and I'm wondering how that gives to.
Well, let's, I think that's because there's an error in the function. Yes, okay. We probably want to do that. Okay, and that will make 2 a prime number. Yeah. Wait, what am I doing wrong?
So.
Oh, wait. That, no. Yes, sorry. Should be the other way around. 1 and 2 are prime numbers. So this shouldn't be like this.
Is 1 a prime number?
Is 1, I don't know. Is 1 a prime number? It is, right? It's divisible only by 1 in itself.
Yeah, but then 2 and 3 and so on wouldn't be prime numbers because they're divisible by a prime.
No, that's not right. It doesn't matter that it's divisible by a prime. No. The definition of, all right. I'm not a math major here, guys. Right? Is 1 and 2 are prime numbers, right? Yes. Okay. So the definition. So to be clear, the definition isn't whether it's divisible by a prime. It's just that it's divisible by 1 in itself. So is 1 divisible by 1 in itself? Yes. Is 2 divisible by 1 in it, and it's only itself and 1? Yes. So those are both prime numbers. Okay, so this is not quite right. What's happening with 2? It's going into here. It does 2 to 2, so it's going to look at 2, and it's going to see that it's
2 to 1, right?
yeah, exactly. It's going to return false, right? Okay, so that's not quite right. Good catch. This is what I'm looking for, guys. Just testing you. Okay, so I'm just going to ghetto fix this. We're going to do if X, oh, we can learn something new here. Great. Okay. So we've been doing these conditionals where I say equals equals, less than, greater than, less than or equal to, greater than or equal to. There's this other thing you can do called, and I do this all the time, this is a very useful thing, percent in percent, which says, is the thing that you're looking at in this vector, okay? So is X equal to equal 1 or equal, this is equivalent to, oh, we didn't talk about the other conditionals. Okay, so there is and or. So this would be equal to X equals 1 or X equals 2. So the line is an or. So the best way to think about this in kind of plain English true. All right, so you can have true and true. So let's say X, Y. Okay, X, Y, X and Y, X or Y. Okay. And all combinations of this, true, 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 false, false, true, false, false. Dang it, no one here is wearing a hat. All right. Someone in this class is wearing a hat, and someone in this class is not wearing a hat. True or false? True. Okay. So for that would be both statements of mine were true. So the and is true. Okay. Someone in this class is wearing a hat, or someone in this class is not wearing a hat. True, right? Okay, so now I need to come up with a true statement and a false statement. Okay, so yes, okay. I am wearing a hat and I am not wearing a hat. True or false? False, okay? So on the and, you have to look at the intersection of both conditions, right? Okay, I am wearing a hat or I am not wearing a hat. True. So in an or condition, if one of them is true, then both of them are true. Okay, so this would look like this. Oh, sorry, false, true, false, false.
X and Y, last one. Oh,
Yes, they're both false, so it's false. This was the best I could come up with on the spot. Okay. All right, cool. So in an or, right, it checks if either of them are true. So that's the x equals 1 or x equals 2 is the equivalent to this thing here, x% in 1 and 2. So remember, it's going to hit the first thing, return first. So if it's 1 or 2, it's just going to end and stay true. Cool. Okay. So we're good with that. Let me go back to this function really quick. Yes. Yes. Yeah, because I'm going to keep that for like 0 and -1 and -2 and so on. And don't worry. Okay, there's another thing. Like it's supposed to be integers. We'll talk about how we can like test that later. Okay, anyone notice anything interesting about this function at all? I know we're kind of wrapped up in interpretation, but let me test. Let's test the number 67. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on and so forth. Okay, wait. Let me make this easier. Let me do 23. 23 is a prime number, right? Okay. So I'm going to go all the way down to 23. And so on and so forth. So this is, okay, hang on. I'm just going to do a check if the mod is not 0, right? So not divisible, not divisible, not divisible, right? And I'm going to keep going, so on and so forth. Okay, do I need to go all the way down to 22? No, you're shaking your head. Why?
So trying to put the right way to say this. You don't even need to check past 5.
Why?
Because for example, 21. 21 is divisible by 3 and 7.
Mm-hmm.
But you don't need to check 7 because you know 3 works.
Yes, exactly. So turns out you don't, it's exactly right. You don't need to check past 5. You don't need to check past, more formally, the square root of your number. Okay. So there is a different version of this function called, hang on, I've got a different version of this function. Is prime better? Okay, and we're also going to do this ghetto thing over here. Great. So this function is the same, except here we go from 2 to the square root of this, and I have this function called floor, which just means round down. There's 2 handy other functions, floor and ceiling. Floor means round down to the nearest integer, and ceiling means round up to the nearest integer. So the function's identical except for this for loop, where instead of going from 2 to x, I go from 2 to the square root of x rounded down. So if I go from, if I want to test 10, I have to check about 10 numbers in the first one and about 3 numbers in the next one. If I go up to 1,000, I have to check about 1,000 numbers in the first one and about 30 numbers in the second one. And so you can see there's a really sort of non-linear exponential sort of savings in terms of efficiency. And so let's kind of take a look at what this means in practice. So I'm going to pick an arbitrarily large prime number. So remember, neither of these need to go very far to check if it's like divisible, if it's like an even number or something, right? Because it's divisible by 2 and then it ends. But if you picked a really big prime number, such as 99,999,989, which is a prime number, let's see what happens. So what I'm doing here is I'm doing a little function called sys.time. And that is a way that I can measure how long it takes to run a function. This is a good way to test for like functional efficiency. So I saved the current system time in a variable called start, and then I just print the current time minus the start that I saved before after I run the function to see how long it takes to run it. So let's see what happens. So I'm just going to select all of this and I say go. Okay. I forget how long this actually takes. Hopefully not that long. So what this is currently doing is that it is running through this for loop, right? And it's checking all of the numbers n from 2 up to 1 minus this number. And the second function will do the same thing, except it's going to check from 2 up to the square root of that number. So the first function took 28.3 seconds. The second function took 0.004 seconds. So what is that? 28 divided by 0.004. So the other function was 7,000 times faster. Okay. Yeah. There's a concept called big O in computer science, which has to do with essentially the computational time and efficiency it takes to run an algorithm. And what we call, so this first function scales at a rate of n, which means as your sort of input grows by some amount, the time that it takes to run that function grows in a sort of linear fashion. Whereas the second one, as I get bigger and bigger, it doesn't grow linearly. It grows with the square root of that, right? And so this is some kind of log n or root n, sorry, big O. Okay, so this concept is important to kind of keep in mind as you guys run into big data problems, which is possible in this class, depending on what data sets you're working with and what projects that you might want to do. Keep in mind that oftentimes you can try and do things a little bit more efficiently rather than just waiting around for your computer to spit out an answer. Okay, any questions about this? Okay. So what I'll say, one other thing that I'm going to mention, but I'm not going to go into for class is that one of the reasons why this takes a long time is that for loops are actually not that efficient in R for some complex reasons I'm not going to get into. There are actually more efficient ways of doing for loops called apply. There's a whole family of functions called apply that will do for loop type of operations more efficiently. It'll kind of parallelize them in some instances. It's a little bit more complex, but generally those are more computationally efficient ways of running for loops. But for loops are way more intuitive and most of the time are going to be pretty fast anyways. You're talking about, saving seconds on the order of seconds or tens of seconds, hundreds of seconds, that sort of thing. If you do start running into those issues with for loops where it is becoming inefficient, then I would encourage you to look into this class of functions. Yeah, so just as a heads up, and maybe I'll put a sort of primer online for that. Okay. So we've kind of skirted around this today and the last lecture, but it's time to talk about data types. So we're going to talk about two things, data types and data structures, and get an understanding of what all the different kinds of things are. in our data types. This is a number. Great. So we'll do that. We've seen this before. Okay, so I've defined an object called this is a number. I've assigned it the value 1, and I can test whether or not this is a number with this function is numeric. And voila, true. Great. We know this is a number is a number. So remember before we saw this L thing happening. What the heck was that about? This is an integer, 1L. So this L is a designation to let R know that the number you're defining is a whole number, integer. So the way I test that is integer. This is an integer. And true, great. What do you guys think? Is dot numeric, this is an integer. True or false? Yes, there. False, we have a bunch of falses. True. Integers are numeric numbers. Is dot integer, this is a number. True or false? False. Numbers are not integers, but so not all numbers are integers, but all integers are numbers. You have to tell it that it's an integer for it to assign it as such. And so without the L, it will not return true. Great. This is a character. Hi. Is character. Probably true, right? True. Okay, and I'm not going to go through it. If you test hi as a number or an integer, it'll be false. So we've got 3 guys so far. Number 2 is probably going to be a little bit less common. I don't use integers that much. Maybe you will. Who knows? But characters and numbers all the time. Another one that is also extremely common. This is a logical. True. Is dot logical. This is a logical. True. You could also do this is a logical false. And is logical would be true. True and false are your 2 logicals. Great. Also very common, use this all the time, not like explicitly, defining things as true and false, but logicals are, as we've already seen, right, kind of blended into lots of different things. Okay. Last one, I have literally never used this except every year, once a year, right now in class. Square root as complex minus 1. This is 0 plus 1i. Does everyone remember what this means? Algebra 2. So yeah, it's an imaginary number. Square root of -1. So you can do that. I've never done it. But there you go. We're going to be complete here. So is complex. This is a complex, and that's true. Great. And that's all I'm going to say about complex numbers. Okay, so there are 5 different types of data types in R, and there they are: your numbers, your integers, your characters, your logicals, and your complexes. Probably more interesting are the data structures. All right, so we are going to get more interesting now. Vector 1. So we're going to look at a couple different vector types. 1, 2, 3, 4, just like before, is numeric. What do you guys think? True or false? We say we got a true and we got a false. Great. All right. One of you guys is going to be right. True. So interesting. You can see that for a whole vector, you can determine whether that all the entries of that vector are going to be a certain data type. Okay, and this will be important in just a moment. One other thing that I guess we haven't really talked about yet. If I want to reference a specific thing within that vector, I can do that. So if I want to look at the third entry of the vector, I can call it using the square bracket notation, which is going to get pretty common soon. So, oops, sorry, vector 1 is the name of the object. And if you want to refer to things within this vector and eventually within like a table, we use these square brackets to refer to locations. So 3 means the third item of the vector, which is also 3, coincidentally. So if I hit enter, it will return 3. Great. All right, any questions so far about vectors or anything else? All right. Next guy, vector 2. A, B, C, A, B, C, D. Great. So is dot character vector 2 and is dot numeric vector 2. What do you guys think? First one is character. True. How about the second one? False. Awesome. True, false. You guys got it. Same thing here. If I want, let's say, the fourth item, which is going to be a D, vector 2, square bracket 4, and I get D in quotes down there. Great. All right, let's mix it up. Literally. 1, 2, C, D. Great. Now I have a vector and vector 3. All right, no cheating. Don't run it. What do you guys think? Let me move my mouse out of here. Okay. True or false is numeric? True. We got a true and a false. Great. 50-50. Is character true or false? False. Okay, we got a bunch of falses and one true. Okay. All right. Your whole grade depends on this. It's not numeric, but it is a character. What? Okay. All right, so this is why this is important. Vectors are only allowed to have one data type. So let me do this. What do you guys notice about this? Vector 1, enter, 1, 2, 3, 4. Vector 3, enter, quote 1, 2, CD. So here, what you'll notice is that the numbers have been transformed into characters. Very important to remember this, because one day you're going to load a data set and it's going to be like, you're going to have some kind of like survey that's going to be, oh, this person's, what is your income? And then people are going to enter, 50,000, 70,000, 120,000. And then someone's going to enter A. And then you're going to try and like multiply something against that vector. And it's going to be like, what the hell are you doing? And you need to check for things like this, because it turned all your numbers into characters and you can't multiply anything against a character. Okay, so also, right, if I do something like is dot numeric vector 3 entry 2. All right, what's the second entry of vector 3? It's 2. So is this going to be true or false? It's going to be false, because remember, it's not a number, it's a character. Great. So this is kind of like all characters are characters, but not all numbers are numbers. Numbers can also be characters. Okay, so we've mainly been dealing with sort of one-dimensional vectors, but you can do two-dimensional vectors, which are called matrices. So the way that I do that is with matrices. So matrix 1 is going to be the matrix 1, 2, 3, 4. And I will have 2 rows and 2 columns. And let's see what this is. So I'll just say that matrices and the next thing that we're going to look at are principally the same as vectors. So you can only have one data type as before. So all the things that we're saying about putting numbers and characters, if you do characters, the whole matrix is going to be a character. But with just numbers, you can do as numeric of matrix 1 and it will return true. Let's look at what matrix 1 looks like. So matrix 1. Okay. 1, 2, 3, 4. It will go row first, then columns. So it goes row 1, row 2, then column, starting column 1, column 2. So whatever you put in here, it's going to fill it out in that order. So row, column. That's going to be important to remember for like everything. Everything goes row, column, okay? When we do references, in matrices, in data frames and data tables, row, column. RC cola, however you want to remember it. It's going to be like this. Okay, so let's say I want to take a look and return the second row, first column entry, I want to return the number 2. How would I do that? I would do the same thing from before, where I use square brackets as a reference point, or as to call out a reference point. And I want to look at row 2, so 2, comma, column 1. Okay, and command enter, and it returns 2. Great. We can also do a matrix. So we've done a one-dimensional, which is a vector, a two-dimensional, which is a matrix. We can do an n-dimensional, which is known as an array, which is just a generic term for any sort of vector matrix of arbitrary number of dimensions. Okay, so for an array, array 1. So let's do array. I'm going to do 1 to 8. And yeah, you can kind of think of this as like matrices that are stacked on top of each other, and then you can have more and more dimensions of that. They get sort of hard to visualize after a while. So the dimensions are going to be 2 by 2 by 2. So it looks like this. And array 1 will have like 2 matrices, right? Kind of like back to back, if you can kind of visualize that. So then the first one looks like this, and then the second one looks like this, all right? So if I wanted to call the, let's say I wanted to call 7, the number 7, how would I do that? Hang on. Array 1, sorry, so what was it? 1, comma 2, comma 2. Great. So row first, so row 1, column 2, and then second thing, whatever. Yes, that's right. So if I hit enter, great, I get the number 7. So, okay, I sometimes use matrices. It's pretty rare. I don't really commonly use arrays, but they are available if you're doing lots of complex linear algebra. Yeah.
If you wanted to look for a certain value instead of indexing that way, can you, like, you had a really long string that will show up, like, and you wanted to find where something is.
Yeah, you can. In an array.
Or in a matrix, like,
Huh? Oh, or in a matrix. Yeah. How would you do that? Let's see. Yeah, but it's a little, less straightforward here. I'm gonna get back to you on that one. Yeah.
can you, like, do good or something?
You can. Yes. Yeah, that's so. That would have been, so like my kind of brain jumps to that at first, but it's like, if you need to search for it, doing for loops is like an awful way of doing searches, because it takes a really, really long time. So you can imagine as this gets bigger, yeah, that would be pretty troublesome. So for loops is definitely a way to do it. And actually it's really good exercise if you want to right? Figure out how to write a for loop to do it. But there's definitely more efficient ways. I just have to think about how to do that. Let me make a note of that actually. Okay. The next data structure that we're going to look at is something that I do use a lot more commonly than with any of this stuff. And this is called a list. Okay. A list is just this giant thing that can gobble up anything that you want to throw at it. Okay, so you can put any objects in here. And unlike vectors, matrices, and arrays, it can handle different data types. So why don't we make a list of the things that we already made? So list one is going to be a list, and the items I'm putting in this list are vector 1, vector 2, vector 3, matrix 1, array 1. Great. What the heck just happened? Okay. So let's just take a look at what this looks like. Okay. So what you'll notice is that I type in list 1, hit enter, and it spits back all these things, right? Vector 1 was 1, 2, 3, 4. Vector 2 was A, B, C, D. Vector 3 was 1, 2, C, D. Then we had a matrix and then the array down here. And you'll notice that it has this sort of double square bracket thing going on. And so these are the ways that it denotes the items of the list. So this is the first item of the list. This is the second item of the list. This is the third item of the list, and so on. And you'll also notice, right, that it preserves. So these are characters, but these are still numeric, right? It doesn't have quotes around the 1 and 2. And then your matrix is still numeric, despite the fact that within the list, we do have a vector of characters. So the list is more sort of mutable in being able to handle lots of different data types. Actually, I don't know what happens if you do this. Probably it's not going to like it. Oh, okay. Well, I guess. So this is probably also going to be false, I'm going to guess. Yeah. So they'd all have to be consistent. So, okay, let's say I want to call out vector 1 out of the list. You can do that by doing list 1, double square bracket 1. Okay. And that returns the entire thing in that first item. What if I wanted to get the letter C out of the second vector? Well, then list 1, oops. So if you do list 1 square bracket 2, it's as though you've typed in vector 2. Okay, it's essentially just pointing to that same reference. So then from there, if you wanted the letter C, which is the third entry of vector 2, let's just pretend that I typed vector 2 instead of list 1 square bracket 2. So then I would do square bracket 3 at the end of vector 2, right? And that returns the letter C. So effectively, list 1 square bracket 2 square bracket 3 is exactly the same as this. Okay. Great. All right, now it's time for my least favorite data structure, which most people think is a data type, and it's not a data type, it's a data structure. I don't know why, it should be a data type, and it's really confusing. And if you ever get errors in R, probably 90% of the time, it's because of this. So pay attention, factors. Okay, what the heck is a factor? If you work in R and you never go through life with a error related to factors, then you are a damn dirty liar. And anyone who's already familiar with R knows this to be true. Okay, factor. This is a factor. Huh. Okay, so let's look at factor one. Kind of looks like a factor, but wait a minute. Don't characters usually have quotes around them? No, not if it's a factor. Okay, so then is character factor one? No, it's not. Is numeric factor one? No, it's also not a number. So what is it? It's, oh, oops, not one. It's a factor. Okay, what is the point of a factor? So if you are doing some kind of like quantitative analysis, if you're running some kind of regression of some kind, and you feed it, let's say, you feed it something with a character. And this might actually be something you want to do, right? Like, let's say you're working on a survey, for example. What are those questions called? The Likert scales, right? So it's no, kinda, it's like no, probably not, maybe, probably yes, yes, those kind of questions, right? You might imagine you want to do some kind of like regression or data analysis on that, and you try and feed that in, and it's going to be like, you want me to do math on a bunch of words? What? So the reason why you have factors is that you can designate designate these like characters as sort of categorical properties. Okay. Not only that, you can order them in certain ways. So for like a Likert scale, right, there is some kind of order inherent to those characters. By default, it's going to be alphabetical, but you know, even the example that I just gave, the no, probably not, maybe, probably yes, yes, right? That's not an alphabetical order. So you can actually define the order that you want using this levels command here. A factor is this. Okay, so if you let's see. So if you look at the order of the factors, let's do this. So the levels of my factor are a factor is this. And then you can see how many levels there are, and levels factor one. There's 4 different levels. And the order is defined by the level. So factor one, it'll be 3, 4, 2, 1, right? Because this was the first item in this factor one, but it is the 4th level. Wait a minute. What am I doing wrong here? order factor one. Oh, no, okay, sorry. It would be reordering everything. So it would put, if you wanted to put this into the order based off of the levels, then 3 is first. Wait, sorry, A, sorry. A would go in first, and then factor, which is in your 4th place, would go second, and then 2, so is, which is in your 2nd spot, would go there, and then this would go last. So it tells you the order that it should go in. Okay. Yes. So it'll store the thing in, it'll store the factor in whatever order that you've specified, but there's like, it knows that there's a ranking to the words, and it'll keep that in the back of its mind in case it needs to ever do anything with that. So if you type factor 1 here, it's not going to like reorder. It's not going to reorder this vector, or sorry, not sorry, this set of factors into anything. It'll keep it in this order, but it knows that the actual like levels for this looks like this. Does that answer your question? Sort of. Okay. Yeah, factors are weird, but they are useful, unfortunately. When you load in data externally in the default reader, usually it's going to be loaded in as a factor. So remember that, because you will probably run into issues with that. Okay, let's see. So let's revisit vector 2. So I'm going to do something here. I'm going to overwrite one of the entries. So in addition to being able to reference something, I can point to a location and not only say, what is it? I can say, replace it with, let's say, blah. Okay. And we'll look at that in just a second. I'm going to do the same thing to my factor. Replace that with blah. Oops. All right, I got a warning message. Don't worry about it. We'll look at what's happening in a second. Okay, vector 2, enter. All right. I used to have A, B, C, D. Now I have A, blah, C, D, because I said go to that second entry and assign blah to it. Cool. Straightforward. Makes sense. We're all good. Factors. Why? This NA, A factor. So I tried to replace the second entry of my factor with blah, and instead I got an NA. So when I initially define the factor, I get to call these levels here. And now you've put in a new character here, and it doesn't know what the heck that is, right? Because these are like categories that you've already defined. You're putting in something that doesn't belong to any of the categories. So it says, I don't know what this is, NA. So if you went back And let's do something like this. So if I copy this and paste it down here, and then I add another level, and then factor 1, look at this. So this is a factor, same thing, nothing's changed, but now blah is one of the levels at the end. So you don't need to have all the categories of the categories that you defined within the factor. But now when I change it, factor 1, entry 2, blah, and I take a look at my factor 1. Now it works because I have defined that category, and so it's no longer an NA. Any questions, confusions? Yes. So on the initial sort of load in or something, however you've instantiated it, that's where it'll kind of define it. So you don't even necessarily need to define it yourself, like especially like the most common time this happens is like when you load in data. So it'll put in all those factors for you. But if you want to add more factor or more levels into the factor, you can do that. Yeah. Any questions?
How do you add levels after we have defined?
Yeah, good question. I was just thinking that. I'm not sure. Does anyone know how to do that? So, okay, I know how to do that. I'm just kind of thinking about whether or not there's a more efficient way. What I would do is, okay, actually, let me just use this exact example. So if you ignore lines 112 and 113 and we wanted to add that in, so what I would do would be this. Factor 1 is factor 1 levels equals C of levels of factor 1 plus the thing that I wanted to add. So let me walk through this really quick. All I'm doing is I'm recreating the factor. And the way we do that, right, is you tell it what the things are, and then you tell it what the levels are. So I've recreated the factor, and then I've added in, when I'm defining levels, the existing levels of that factor plus what I want to add. That's how I would do it without Googling anything, but I suspect there's a more efficient way of doing this. Let me make a note of that and I'll get back to you. So let me. Yeah, that's actually exactly what we did here. It should be the same thing here. So you are allowed to define categories that aren't in the factor.
Yeah, but there's
In here, this is a factor, so there's no blah in here, but we still made it a category. Yeah, and so that's what you see right here. So the entries of factor 1 is this is a factor, but there's no blah, but you can have that category.
but either, yeah, I'm thinking, now when we kind of create a problem, we have more levels than parts. Like,
No, that's fine, but you can't have more parts than levels. Well, you can, but you would have NAs. Yeah. Okay. So you guys are all good. There will never be any warnings or errors for you guys for factors. I'm blessing all of you. Okay, so now on to probably the most useful stuff. data frames. So if we think about the sort of analogy to something like Excel, like your Excel table is going to be your data frame. Okay. So this is what I would just call like a generic table. So let's kind of figure out how to make one manually, which you'll do, but probably more commonly, you know, this is going to get loaded in as data, but it's still good to understand how this is made. Okay, data dot frame. Okay, so the generic sort of way we do this is so data dot frame, and then it's your column name. Let's say X equals, and then it's whatever you want to put here, and then your next column. Let me actually just explicitly call it column. So we'll do column 1, column 2 equals dot dot dot, column 3 equals dot dot dot, and so on. And then you sort of close your data frame. Oh wait, that's a comma, not a. These are commas, and then close your parentheses. So here I'm just going to make a sort of generic thing. So it's going to be student, student 1, student 2, student 3, ages equals C 24, 25, 27. We'll do gender. Something like this. Math dot score equals 600, 660, 780. Verbal dot score equals. Oh, what the heck did I do? Over here, sorry. See. 500, 620, 800. Great. Is there an error? There was an error. God dang it. All right. Oh, I just needed to close that out. Okay, as you can see, it's kind of a pain to do this manually, but here we are. Okay, so all I did was I just made this little table here. We've got 5 columns: student, ages, gender, math score, verbal score, 3 students, 1 in each row with corresponding of each of the entries here, right? Pretty straightforward. Okay, so let's talk about what we can do here. Useful functions for tables or data frames. So probably less exciting, but for larger tables and data sets, some of these higher level functions will allow you to quickly examine the contents of it without kind of like doing all this complicated stuff. So summary is one common one that I use. So what kind of things does this? Oh, yeah.
Why did you use quotes for gender? I didn't use quotes for
Yes, that was definitely intentional. No, that wasn't as an accident, but actually, as you can see here, it actually doesn't matter. You can use, you don't have to use quotes to define the column name. It's a force of habit for me. But as you can see, you can go with and without quotes. Okay, so for a summary, you can see here, it'll tell you for characters, kind of what's going on. Let's actually do, let me actually do something different. It's gonna screw anything up. No, probably not. Okay. So I'm actually gonna do factor for gender so that we can see what the difference is. So I'm going to rerun that. Okay, there again, and summary. Okay, and it should look a little bit different. That didn't do what I wanted to do. Okay, yeah, okay, sorry, I have to do this. Okay. Yeah, okay, great. Okay, so you can see one of the big differences here. So, okay, for the numeric stuff, it gives you this summary statistics, min, first quantile, median, mean, or sorry, quartile. Yeah, third quartile, max. For characters, it'll just tell you how many entries there are and what class it is. And then for factors, you'll notice that like it knows, for example, that this is one category, right? Because it's the same thing. Whereas a character, you know, it doesn't really matter if they're the same or different. Okay, great. So that's what you would see there. If I want to explicitly see the data types, you can do str, which stands for structure. If I run this, okay, it tells me this is a data frame. There's 3 observations and 5 variables, right? 3 rows, 5 columns. Student is a character type, age is numeric, gender is factor with 2 levels. Math and verbal are both numeric. Okay. So let's talk about referencing the table. So if I wanted to look at everything about the first student, remember row column, I'm going to look at the first row, and that returns all the information about the first student. Okay. If I wanted to look at multiple students, I can do that as well. Student data 1 to 2, comma. So that creates a vector 1, 2. So it's going to look at the first 2 students. Great. Let's say I just want to look at the ages of my students. I can call the second column. Oh, yeah.
Like if you were to do it without, so like you gave it and you just did
Mhm.
direct it on the
Okay, yes. Yeah, so your question is more complicated than you think, but generally, okay, so the comma is just as a way to denote if I'm looking at rows or versus if I'm looking at columns, right? If I don't have the comma, like, are you referring to the row or are you referring to the column? Okay, so if I do student data 1, so here it'll default to the column, but maybe that's not what you wanted. So it's typically not, it's not good practice to do this. And sometimes you're actually going to run into issues where it's going to break if you try to do it like this. That's what I'm going to say for now. I'm going to take it back in a little bit, but that's what you should have in your mind. Just put the columns because they're important kind of placeholders. Yeah.
It might be the same as my question earlier. If you want to find who had a score greater.
Yes, so this I can do. All right. So and this is also very common to want to be able to search for something. So we're gonna get to that in just a second. Okay. Yeah. The reason why that question was a little bit more complex for like matrices and arrays is because the dimensions are kind of weird, right? For an array, like I was trying to figure out a way to tell you in a generalized way, but like, what if you had like a 7-dimension array? It might be, yeah, I'm not, you'll see like when we look at the filtering for within a table, it's a lot easier because it's just like a 2D object and it's always going to be a 2D object. Yeah, so I'm going to show you in just a second. We'll get there. Okay. Yeah, that's all part of the set of things we're about to do with here. So these are the square brackets, right? I've described as ways of referencing into the table. And that includes being able to look for objects with or specific entries in the table. So we'll get there in just a second. Although we are running out of time. All right, so student data comma 2, second one returns all of the ages. And then if I want to look at like a very specific entry, if I want to look at the age of the third student, right, that's 3, 2. Great. So that's the basics of the square bracket function as we've talked about so far, right? Referencing sort of entries by row, by column. Okay, but we can do a lot more than that. We can call a column by the name of the column, math.score. And the way that you do that is with this $ operator, which indicates you to look up a specific column name. And I'm going to hit enter. So this is the same as though I did student data square comma 4, right? That's the math score column. Student data. I can also look at it. So instead of calling the number of the column, I can call the name of the column in the position there as well. So quote math.score. If you don't have quotes, it's not going to work for data frames, but we're going to get into a different type of table. Okay, anyway, don't worry about that for now. I'll take some of this stuff back in a bit. So quote math.score, and this will also give me that column. One of the nice things about line 129, so the thing I just did as opposed to the last one, is I can call in multiple columns if I want by name. So I'm going to, oh, why do I have a period there? C, I want to do age and math.score. And what did I do? Uh-oh. Oh, sorry. What is? Oh, it's ages. Yes. Thank you. Okay. So in this case, now I can return multiple columns. You can't do that with the dollar thing. And I can change entries as well, kind of like we were talking about before, as we did replacements. So 2 comma verbal.score. And if I want to change this to 600, I can do that. We can see the previous verbal score for the student is 620. And so if I do this, and then I look at the data again, great, we're there. Okay, so now doing this filtering. Okay, so let's say I want to look for an entry. Okay, let's say I want to identify a specific verbal score. Okay, so if I want to just look, dot score. So if I do this, it returns 500, 600, 800. Great. And oops, student data. Okay, so I'm gonna try and walk through this step by step. So if you want to look for an exact entry, I can do an equals, or I can look for multiple things. If I do something like less than, I'm just gonna do less than 510 right now. So, all right, what do you guys think is gonna happen if I hit enter? What type of result is gonna come back? Sorry? Not quite. So anytime I'm doing one of these conditional operators, less than, greater than, equals, what did we talk about before? Like what were the types of things? Yes, logicals, okay. So this is gonna return a true or false, but you're doing it on multiple items. So is the first entry true? Yeah, or is the first entry less than 510? Yes, it is true. Otherwise, false, false. Okay, so that's the first step. Let me show you guys something really quick. So logicals can actually be used to reference positions in vectors. So if you guys remember vector 1, or let's do vector 2, right? This is A blah CD. So vector 2, and then if I reference false, true, true, oh, sorry, false, and I probably have to do a C, okay. False, true, false, true. It's going to return all the trues. So first entry is false, nothing. Second entry is true, blah. Third entry is false, nothing. Fourth entry is true, return D. So this is a really sort of powerful tool because it's going to let us manipulate the less than 510 thing that we just did, the true, false, false. And if I take this piece here, and then I look at my reference point here. Okay, so let's walk through this step by step. We know this thing here is going to return what? True, false, false, right? True, false, false. And if I use that thing as the reference for this, what will this return? Yeah, so it's going to return the first entry. So this is the way that we filter and look at specific items in your data frame. Okay, and so I can hit enter here, and it will return that specific entry. And so the answer to the question, right, of referencing specific values, this is how you would do it. And you can do it with an equals equals or a sort of different type of conditional. And then it will give you this sort of information as a way to locate where that is within the table, right? You can imagine like maybe this data frame were many times bigger, that there were like 10 million students in this data frame, and I couldn't like just look at it and know. You can still run this sort of operation and instantly grab all the guys who are like less than 510 for the verbal score. And in fact, I can even replace that value, right? And do assignment operators on whichever ones are there. So if I did this, it would replace 500 with 520. You could do it to multiple things. If I instead change this to greater than, let's say, yeah, let's just say greater than 550, I will overwrite multiple columns. And all those guys that had scored above 550 now get reassigned to 520. Okay, we are out of time, so that's where we're going to end for today. That's pretty much a basic rundown for your data frames. Yeah, let me know if you have any questions. Otherwise, I will see you guys on Tuesday.
One is assigned.
Yeah, so homework 1 will be assigned start of Tuesday, and then it will be due on the end of Thursday, the week afterwards. So you have 9 days. Yep.